Good morning, everyone. My name is Abdelhady Omar. I am a risk management specialist at Hatch. I'm going to present this paper. It's a component I did through my PhD, co-supervised with co-authored with Professor Osama Moselhi. It's about the improving the accuracy of information extraction from bridge inspection reports using large language models, specifically pre-trained or fine-tuned pre-trained generative transformers. So deterioration of bridges can pose significant risks to public safety and impede economic activities, and they can lead to catastrophic failures. Specifically, the deck of the bridge deteriorate more rapidly than other components due to direct exposure to chemicals during the winter and direct forces from traffic and so on. The symptoms of the deterioration of the bridge deck arise in the form of surface or subsurface defects, like as we can see here, corrosion, spalling, this hole, and delamination, scaling, and cracking. Data about this different type of defects are collected during bridge inspections, and they can use afterwards in developing deterioration models, condition assessment, plan for needed intervention, and budget allocation. But the point is how this data was collected and stored, and is this data in the right format to be used directly in data analytics tool or application of artificial intelligence, machine learning, and this is stuff to develop smart asset management tools for bridges? So let's have a look how this data is stored. The case study is from the Ministry of Transportation of Québec. This is a typical inspection report from the ministry. It includes some administrative information, photo report, and inspection data that represent comments provided by inspectors during the inspection process. So let's have a closer look on the comments that provided by those inspectors during inspections. As we can see here, it contains useful information about, for example, each bridge component. Here, let's have a look on the bridge deck. This is the bridge deck, and the elements of that bridge deck, including the wearing surface drainage system, exterior sides of the deck, and the structural slab, and the condition of each element, and comments about the type and the severity of each type of defect, like, for example, cracks, the size of cracks, if there is, for example, light scaling, and so on. But the point is, this is a snapshot of one page in a 50-page report in a network of 9,000 plus bridges. So how we can collect this data, transform into a useful format that can be used in data analytics and develop asset management tools, for example. So the first thing here, the first step is to collect this data from different sources, hundreds of inspection reports, and store it into one repository. So the first step, we collected this data first. We annotated the reports for the useful information that we need, developed rules to extract this data, and check this data if the collected data is captured correctly or not. But not only the process of data extraction was challenging from this large number of pages and the reports, but also how to retrieve this reports from different sources that is stored in. So retrieval of this reports, and also we developed the algorithm how to prepare this reports, for example, exclude unnecessary pages to reduce the complexity of the process, exclude images if we are not going to process this image, and again dispatch this reports into the algorithm that will make data extraction from this process. And for more information about this different algorithm that's published already, so you can reach it through Automation in Construction Journal. After collecting this data and storing it into one repository, we were able to collect all this data from about 2,000 plus reports into one Excel sheet like this one. But this repository doesn't contain only data about defects, about delamination, spalling, and this, but also it has another data about the dimensions of the bridge, average daily traffic, route class, and so on. So let's have a look at this Excel sheet. So now instead of having a large number of inspection reports, we have it in one sheet. This is the ID of the bridge and the section of that bridge component. This is the deck, and the element of that component, if it's the exterior side, if it's the drainage system, wearing surface, and so on. And the comment, this is the comment is here. But still, again, we collected it into one repository, but we cannot use it in that data analytics or condition assessment or predicting, for example, probability of failure and so on. So what we need to convert, we need to extract the existing type of defects along with the severity of each type, like this. So at the end, we need to reach something like this format. So for each section, I need to know what defect type exists from corrosion, cracking, delamination, scaling, and spalling. And then what is the severity? Is it moderate, slight, significant, or severe, and so on. To convert this data into this format, two methods actually was used. The first one is the conventional natural language processing and text mining using tokenization, lemmatization, and so on. And the second method is the use of large language models. And for the large language models, two models was used, the baseline one without any fine tuning, and the second one fine tuned with a specific data from our inspection reports. And the most challenging part in using the large language model is to develop the right prompt or high quality prompt that can be transform this data into consistent format that you need. This prompt actually should contain the different type of defects that you need to extract, the severity of this defects. You can give examples in the prompt so the model can see what is the input and what is the output that you need, and so on. And after finalizing this prompt, the performance of the model was low. So we thought about to fine tune this model before use it. Fine tuning with specific data from the inspection reports again that we used. And this fine tuning process include selection of data of fine tuning and divide this fine tuning data into fine tuning and validation to check the accuracy of the fine tuning process, and define the fine tuning parameters. And the comparison between these three models, which is the conventional natural language processing model, baseline generative pre-trained transformer or large language model, and the fine-tuned one was not only based on precision, accuracy, recall, but also consistency of the output, stability of the results, ease of use, and coding resources needed, and so on. This is one example that sent it to the model. This is one example, and this is the output. As we can see, it's consistent through different example, and here we can see the performance, the difference between the performance of the three models. We can see that baseline GPT here, baseline generative pre-trained transformers were lower performance than the natural language processing one and the fine-tuned model. And actually in all defect type in corrosion, cracking, delamination, the fine-tuned model outperformed the baseline one and the conventional natural language processing model. But again, the performance was the fine-tuning model, and the conventional natural language processing one was close to each other. In some instances, like in detecting spalling, for example, there was a significant difference between the performance of the baseline generative pre-trained transformer and the fine-tuned model. So the next question, what is the potential uses of this? What is the potential uses of this data that is already collected from large number of inspection reports and transformed into this format and augmented with other data like average daily traffic, route class, and so on? This is the different components that I developed through my PhD. So we used this data to develop data-driven condition assessment models, and also to determine the probability of failure. So based on the severity of these defects, we can over time predict the probability of failure of the bridge deck. That enabled us also to integrate it with the consequences of failure and develop a bigger risk of failure model, and also to investigate and develop non-destructive evaluation effectiveness model. So if we know the historical severity and the type of defects that exists already in the bridge, so we can allocate what type of non-destructive technique like ground penetrating radar, infrared thermography can be used for this specific type of the bridge. And we developed a cost model for the bridges that includes the direct cost of the inspection method and indirect costs like delay cost due to deterioration of the bridge, vehicle operating cost. At the end, we were able to determine from large bridge networks that have about 2,000 plus bridges, we were able to determine which bridges should be inspected first to prevent further deterioration. When this inspection should be conducted. So is it this bridge need inspection now in the next 2 years, the next 3 years, and so on? And which inspection non-destructive technique is it? Ground penetrating radar, for example, most suitable for this bridge, infrared thermography, or even just visual inspection is the most suitable method in this case. Thank you so much.